Right. Well, welcome everyone to this meeting of the virtual CICS user group. Excuse me. I'm Trevor Eddles. I'm CEO of iTechEd Limited. We're a mainframe consultancy, analysis and technical authoring organisation. And we're responsible for the content on the virtual CICS website, and we produce the newsletters. And we also look after the virtual IMS user group. So let's start by running through today's agenda. As usual, most of the meeting will be taken up with a presentation. And today our guest presenter is Tom Dunlap, CTO at Themis, Inc. And his presentation is called the CICS MQ Interface. A copy of the slides from this presentation will be on our website later today. And if you missed our previous meetings, you can download copies of those presentations from our website too. And our website is fundy.com/virtual CICS. That's all one word. You can listen again to the whole presentation. There's a link on the resources page of the user group. So fundy.com/virtual CICS/resources.htm. Following Tom's presentation and any questions you have for him, we'll move on to the latest CICS news and the latest CICS-related articles. Feedback requests is there to remind me to ask you for your feedback about this virtual meeting. And then I'll give you the dates and times for the next virtual meetings. So that's the plan. And I'm anticipating that the meeting will last just about an hour. Okay, as I just said, today's presentation is from Tom Dunlap. Tom has been working with CICS since its first release in April 1969. And throughout his career with CICS, he's developed applications, worked as a systems program and administrator, lead architect for commercial software products, which worked in CICS, and provided both applications and systems level training to many corporations. And the list of his experience goes on for a long time. So Tom is a very experienced person. If you want to read the whole thing, it is on our website. But what I'd like to do now is Tom, thank you very much for being with us today. And let's see if I can pass control back to you. Let's see if I can go participants. Right, you should have a message that you're now the presenter, Tom.
Yes, I do. Okay, let me bring up my PowerPoint here. And a couple of minor adjustments before I get going. Okay. So everybody can hear, I hope, and let's kind of move on. The presentation, as Trevor says, will take about 50 minutes, 55 minutes at most. Initial screen here, you'll see my email, by all means.
All right, Tom, I can't see your slides.
Oh, I know why. Bear with me. I forgot to do the share.
Yeah.
Now, hopefully we'll get this straightened around.
Yeah, all good.
Huh?
All good, I said.
Okay. Yeah, it's a hardware problem. Man doesn't know how to use the hardware. Okay. Just one minor adjustment here. I'm going to get this thing out of the way. All right. Now we're in shape. Okay, so once again, back to my presentation here. So there's my initial slide, like I said, I give you my email. By all means, if I can answer questions down the road, send me an email. Now, this is also a presentation I did as a webinar for our company, so you actually see the link there in the webinar. But as Trevor says, you'll get the slides and a replay from YouTube. So, okay. So allow me a minute or two to look at the application, give you a little insight. Not that I'm trying to, make you all application developers, but I need you to at least understand what I'm doing here, what I've been doing with it, so you can make sense out of the later slides and things you'll see. So in MQ, bunch of structures we have to copy in. These are all necessary for any MQ application. And basically, the only biggest thing I mentioned in my notes, when you do get the PDF, you'll see that it has extensive notes. I mentioned about doing a suppress on that copybook. It's 20-some pages worth of COBOL copy code, folks. So basically, it's not something that your developers want to look at all the time. But the other structures are necessary for the normal operation of MQ. Also, a bunch of variables necessary. Connection handles, messages, and things you'll see, okay? So those are just basic things that have to be put in and included. Moving on, you do have to have in your working storages or something, again, I'm using COBOL terms, but they're similar for assembler, PL1, whatever languages you favor. Works in Java also. Anyways, I have to have message areas. Now, talking in terms of COBOL and specifically CICS, one of the problems with COBOL CICS applications is we're cloning working storage for all of our tasks. So basically, I'm sitting here saying if your message exceeds 200 to 300K, and that's just a number I throw out, it really is environment dependent. But if you got large messages in MQ, you're cloning your working storages. If I had a megabyte message defined, I would be cloning a megabyte at a time for every person using the task. So this is a consideration, right, to using MQ within inside of CICS. By the way, the largest your messages can be is actually 100 megabytes. So you can get some pretty big messages. So there I tell you, you may want to consider doing get mains and putting stuff in linkage section, right, beyond a certain limit. And I just arbitrarily throw out the 200K, 300K. Okay, moving on. So on the next slide, I have what is called a put1 call. A lot of notes here. But basically, I'm giving you all the COBOL code necessary to do what's called a put1. Now, put1 is a combination of an MQ open, MQ put, and MQ close in a single call. Ideal for basically putting like a request message to a queue or putting a response message to a queue, but essentially providing the mechanism to work with a single message at a time, okay? So it does all three calls. In the case of CICS, it's pretty typical for the application to basically work with a single input, single output type message. It's fairly common in the applications I've seen. So again, a put1 call, okay? There's a note you'll see towards the end of the text where you'll see it's doing a static type call, right? Specifying the actual name called MQ put1. That is not actually the module names involved in the interface. The module names are actually CSQC, right? In this case, put1. You cannot do dynamic calls. That's a problem with the interface, right? Or the CSS MQ interface. You cannot just simply compile your COBOL programs with a dynam option to convert static calls to dynamic calls. You'll see later on in the presentation, I give you all the actual module names that you would have to call if you wanted to do dynamic, okay? So MQ, right, these modules require being linked to a stub type module to resolve the interface, to get, resolve the entry points to get into the MQ interface, okay? Put1 call. Another very common call, MQ open. If I want to actually do the MQ open myself, this is an example of an MQ open call. And essentially, I must provide the name of a queue manager, or probably a queue that I want to access, and the name of the queue manager. Now, for the most part, you'll see me doing move spaces to object queue manager name. Very good habit I tell developers to get into when I'm teaching them. Object name input here, or MQ-object-I is the queue name, actual queue name. Queue names are 48 bytes, and will follow some kind of standard convention, must be defined MQ before you can use them, right? So I'm gaining access. Now, I don't do what's called an MQ con call. If you've been exposed to MQ in batch programming, you would have done an MQ con call as the very first call. You don't do that in CICS. CICS has done the connection to the queue manager. That's part of the definition you'll see later in the presentation. And that's because the most expensive call in MQ is the MQ con. So essentially, the interface does a connection for us, and the first thing we do is the MQ open. Now, there is integrity or security involved that goes through security checks to make sure that, you know, who's ever doing the application is allowed to access those particular queues. So there is a bit more. This is probably the second most expensive call in MQ, the MQ open. Okay. Next slide, I do what's called an MQ get call to get a message, but I do a little differently here. I'm setting this wait interval, and I'm specifying the option to do what's called MQ GMO wait. What I'm waiting on is waiting on a message to arrive in a queue. Now, it is not doing any active polling or any kind of CPU going on, anything like that. This is simply waiting for a message to hit a queue. And it's going to do what I would refer to as a wait forever if you don't set the interval. Now, the interval here of 20,000 milliseconds basically says it'll wait up to 20 seconds. If it does not get a message, it will give me an error, basically the fact that, you know, no message is available, and will give me the choice of going away or doing something else. Okay. Applications should really never, you know, do a get with wait, let it fail. Well, let me do it again. You know, they really need to do the get with wait for a reasonable amount of time, and if the basically gets no message available, error, if you will, it will they should terminate rather than try it again. You know, I mean, that's what creates the so-called polling situation. They try it fails, they try it again, it fails. Another thing here of note, I'm doing this no sync point. So CICS is the king of all coordinators, but basically this message is not being, you know, I'm basically saying as I get the message from the queue, I do not want it under sync point control. Another way to think of that, it's a destructive get. So if the application does fail, that message is gone from the queue. That's the choice the developers have to make. Okay. CICS will coordinate with MQ for all recoverable things. But if your developers are doing no sync point processing in MQ, then they're taking away the ability for CICS to coordinate with MQ as far as that message is concerned. Okay. So a couple key things I wanted to point out, and that's purposely why I did these calls like this. Okay. Okay, eventually we have to close our queues. So we do a close on a queue. Pretty simple, straightforward. We're closing a particular queue. Now, that essentially releases control of that queue back to MQ for other people to use it. But I could have queues that are defined shareable. Again, bear with me, I'll show you an actual queue definition, a couple key points. So I try to get in all the calls, and I have a little test application that you'll see in Trace. And it was my little test application are doing all these type of calls. But there's actually two different programs, two different transactions you'll see involved. Okay, next slide. So here are the names of modules actually. If I wanted to do a dynamic call, so earlier I showed you to put one call, now I say MQ put one. That is related to a working storage variable, and there's the ones for CICS. So I cannot do the dynam, but I can do dynamic calls where the modules are resolved at execution time. The nice thing about that is I can tweak my code and have it sensitive to working with batch, CICS, or online if I want to. Okay. I can make tests and find out where my environment is, where I'm running, and change the module name slightly. One last key thing from an application point of view, MQ has headers on its messages. About 500 bytes for every message that your developers put into a queue. So the maximum size of a message is 100 megabyte, and what IBM says is allow me about 4K worth of headers. And most I've seen to date is right at about 1,800 bytes on the front of a message. So someday they may hit the 4K limit. What is in the standard header, it's called the MQMD, okay? The message descriptor. And a couple key things in there, a couple key facts here. There's something called a message ID. And the applications need to always set the message ID when they do an MQ put call to put a message on a queue. And there's two ways for them to do it, is either to set the option to message ID none or tell MQ to do new message ID. You always want to generate a message ID. And I'm kind of showing you where the MI here is a message ID, and it's kind of all the same. It works, but I don't have a unique message ID to work with. Okay? Kind of explain that a little bit later, you'll see. When I'm getting the messages, I must also do the same kind of thing. Reset it to MI none. And the reason I say that is when it retrieves the first message, it's remembered that message ID in the structure. So one of the common things I see in MQ going on in an application, an error, if you will, a logic type error, is the application does not reset that thing. So what happens is they skip over because they're looking for a particular message ID and they don't see it. I actually had one application or one company I was working with, and I was training their developers, and the administrators happened to be sitting in on a class, and they were trying to, they had this problem where the developers kept saying, well, MQ doesn't work very well, it's pretty slow, gets one message, and that's all it ever does. Well, the developer was not resetting the message ID, so as a consequence, it would get the first message on the queue, went flying through the rest of the messages on the queue. By the way, there was 1,000 messages on the queue, so it read through 999 messages. Redid the transaction, got the first message on the queue, they were resetting the message ID, went through 998 messages. Get the hint? Now, so I wanted to bring that up because it's a pretty common thing I've seen happen, not just in CICS, but even in batch. Okay? Message ID.
Yeah. Sorry, Tom, can I just ask you a question?
Sure.
Lionel Pfaff has said, is there a measurable performance advantage to using MQ put 1 over MQ open -put -close?
Yes. Basically, it's the equivalent of traversing the interface 3 times versus 1. When you do the put 1 call, you're going between your application and the MQ in one trip. If you do the MQ open, MQ put, MQ close, you're doing 3 different trips to MQ. So it's 3 different trips through the interface. So it's all that extra CPU processing, if you will. Numbers are hard to predict as far as, what percentage of what time, because really it all depends upon what your system is, what your system environment's like. I don't really want to throw out numbers, but it's in a single-digit percentage.
Okay, thank you.
You're welcome. Okay, because I can't see the question and answers myself. Okay, moving on. So message ID is generated by MQ. If the developers follow the lead I give them, which is I tell them about these same options, basically I say use the new message ID, MQ PMO new message ID. And that generates a new one all the time. And it's nice because it can be used as a tracking mechanism. So the message ID is a 24-byte field, okay, and the first 4 bytes is a constant. CSQ blank on your mainframes, AMQ blank on distributed queue managers. First 12 bytes of queue manager name is next. Now, mainframes can only be 4-byte queue manager names. There are formal subsystems are limited to 4-character names. However, on any other distributed queue manager, and I run about a dozen different queue managers on Windows, Linux, different flavors of Linux platforms. And those queue managers can actually be 48 bytes in name. Most people keep them short, okay? So, but IBM says first 12 bytes we'll put in there, and what makes it unique is really the last 8 bytes. It is a binary number that comes from your clocks, your hardware clocks. So every tick of the clock, right, the message ID effectively is changing. Nice tracking mechanism, okay? All right, so I want to get those things out about the application because they're pretty common. Now, this is going to be hard to read, maybe a little bit. So what I did is I did a CICS trace, turned on aux trace, so I capture information. And I wanted to point out some things about what we're going to see in trace. So going back to my slide here, this is an external resource manager. Right? MQ runs as external resource manager interface, or a true, if you will, task-related user exit. So what I highlight first off is this ERM entry, ERM exit. So my application has done the MQ open call that I mentioned earlier. So this is where you can see COBOL application is calling the true, and this exit back from the true. If I take the timestamps and subtract them, you can get an idea of the time involved, 0.064, right? Actually a fairly considerable amount of time. You're talking 64 milliseconds, okay? Now in that amount of time, it's had to go and access the queue, validate security, set up internal control blocks to manage that queue on your behalf, okay, or access to that queue. So we can actually see in trace, right, how long this is really taking. Now, the next thing I highlight is really this. So here's the actual call from the interface to MQ, and you can actually see the queue name involved. Okay, so that is actually when the true itself is calling in to MQ. So we are branching over, if you will, to the MQ address space or queue manager at this point. And of course, on the way back, we can see here's the completion code and return code. Now, MQ, every MQ call has both a completion code and a return code. Completion code has basically 3 different values. It's okay, I got a warning, I got an error. Okay? 0 is okay. If I had a warning or an error, the RC, the response code, would actually have a value in there that would tell me what it is. 2033 is no message available. Yeah, 2050 something is like a connection error, 2085 is unknown object name, and so on. Your developers, though, have labels to work with. However, if I also look now at this times, we can see how long it really took to complete the actual open call. So there is a measure of interface here, right? The ERM entry to ERM exit is the actual MQ interface being processed. But within that, you can see the MQ true entry through MQ true exit, and that's the actual processing over an MQ. So you can actually delineate the differences between the interface and that. You'll notice about only a 2 millisecond difference. So the interface itself within CICS is not a very large portion of the processing. It really is over in the queue manager, right? And that's where basically 62 milliseconds of the code was going on. Again, please remember, the open call is going to have to do security. It's going to have to build control blocks and so on to represent your use of the queue. So that's why it's the second most expensive call. So kind of moving on. So then I did this MQ get call. So again, entry, exit, notice is about 3.5 milliseconds, right? So now we're into a more reasonable thing. We're just going to get a message. And again, here's the MQ true entry and MQ true exit. For the MQ get call, it did work. Code 0. Internally, here's the time for the get. And I did the wrong one here. It really should be this one, but basically it's close enough. Basically 2.4 milliseconds. So again, most of the time is spent truly over in the queue manager. The interface itself is of very little consideration at this point. Moving on, here's a put one call. So, kind of the question. So I do this ERM entry, ERM exit, you can see the time for the total interface, about 5 milliseconds. But we can actually see the put one call. It did work. And again, I got the wrong one bolded, but it's about, right, almost all of the 5 milliseconds. Now that has actually done, right, the open, put, and close. Now it may have taken a little bit less time. I'm trying to remember the sequence of the calls I did, but you know, it did the open call internally, and it did all the validation over there, right? But you can get an idea, right, the differences in the calls. If I had to do the open, put, close, it would be a little bit more overhead, if you will. Again, I'm thinking that this call was done after I did the actual open call, which means the validation to, in my case, rack F was already done by the queue manager. So it took a little bit less time to do the second open, if you will, because it was already validated security-wise. Okay. Okay, so again, I'm just trying to show you what you're going to see in trace. So kind of moving on, here's the get call. Again, I did not bold everything like I should, but there's the entry, exit. Here's the entry to the true. Here's the exit. Now here we got an exception, and you can see the thing here. It came right back, right? So the condition code 2 says I got an error, and this 7fox1 happens to be the number. Well, in this case, actually, I know what it is. If I were to convert that to decimal, it would be a 2033, which is no message available. So I try to get a message off the queue. The queue is empty. Okay. So at that point in time, that get got an error. So I just also wanted to show you what an error looks like. You will see they are generating, it generates CICS exception trace entries when it gets those errors. Again, you really have to convert the hex numbers there to decimal to look them up. Okay. So you can see about 2.6 milliseconds, right, in MQ, and it did not retrieve a message. But you can see the difference here between the actual true time, you know, ERM entry exit versus the actual time in MQ. So most of the time it's being spent in MQ. Kind of moving on, we're going to close our queues. We're done, right? So here's the MQ close. It worked. And again, you can see the times. Okay. And again, I had a bad habit of doing the wrong entry when I bolded it. So the close call took about 6 milliseconds. Most of the time in MQ, 5.8 milliseconds. Close basically cleans up all the in-memory control blocks in the queue manager on your behalf. So it takes a little bit. Now, I will say this. Close calls are not necessary in MQ unless you have done what's called exclusive control of a queue. It's a matter of the way the queue is defined or the way your open options are done. As long as it's shareable, there's no reason to close the queue. Okay? If you have exclusive control, you must close it because that's the only way to release exclusive control of a queue. Okay? Those are options your applications can set. Okay, moving on. Well, the infamous CICS return. Most applications do not do sync point or sync point rollback in CICS. They wait till the end of their task, do the return, and that's when the majority of the coordination happens. Okay? So kind of what I've got here, and again, this is all kind of delineated in the notes, but I'll do it quickly because you don't have the handouts. So here we're calling to do the commit, and of course, way down here, the commit is complete. Okay? Don't get excited about the failed link here. Kind of explain that when I get it to a later slide. So that's point A is the total time in the interface to coordinate between CICS and MQ. Okay? And if I did a quick check, I didn't calculate the times, but 0.346, and of course here's 0.338. So we're talking roughly what? about 8 milliseconds. So not a large amount of time. There's a reason why it didn't take too long, you'll see. Again, I'll show you later. But again, here we can see the true entry, and we can see the exit from that, okay? So basically, well, down here is the actual exit, but we can see the time, point B, is the time actually doing, if you will, the coordinated commit. And point C, right, was the actual time spent in the commit itself. I shouldn't say that. Point B is working with RRS, because it does use the RRS interface to get there. And point D, right, is again, the actual ending of the commit and coordination between that. Again, it's in the notes. So basically, you can see all this happening going on in a CICS trace, and it's all going on typically at return time, right? Again, CICS is going to coordinate with MQ. The other way around is not true. So we do not do what's called MQ back or MQ commit calls in CICS. You must do the sync points or sync point rollbacks. Okay? Moving on. I said I would get this in an hour, and I will, or 50 minutes. So, quick trip through EDF, looking at this. So I wanted to show you work in a trace, show you some highlights about, the actual interface and where it's going back and forth between the queue manager. And you'll see that again in all your notes when you get them. Now, this is my little application. Kind of like to explain this a bit. So this is a transaction I call RT00. Okay? And when I enter it, it comes up with this screen, and it allows me to enter in a user ID, a request, quantity, and or item number and a quantity. It's like a little inventory application. Okay? So this is going to allow me to update inventory, order an item, things like that. I just kind of threw this together so I could exercise and get, the output for a trace and what have you. So this program is the one that does the put one of the request message. Okay? So that put one call I showed you early on, it's doing the put one and different queues for different students. The user ID difference here is when I'm teaching a class for this actually is I use this in my CICS tailoring class, for system programmers. The different user IDs is going to different queues. And this is the way they can test out the interface when they actually define the interface to CICS and work with it. So it's doing the put one, in this case an R is to restock an item number 10 and quantity of 10. It puts a message to the queue and it's going to actually trigger, and I'll explain that a little bit later in the presentation here, trigger a background task. That task, by the way, is transaction QT00. So RT is the user interface, QT is the background task. That program reads the message. It's the one that's doing the MQ open of a queue, the MQ get, and then it physically updates a DB2 table. Okay? And then behind the scenes does that update and then puts a response message back. Meanwhile, this RT program is doing a get with wait, waiting on that message to arrive. Okay? So that's why I kind of showed you those calls. So the person enters these codes, hits enter. They end up waiting for that task to go execute in the background and put a message back. And the moment a message is put back onto the response or reply queue rather, it pops back up and populates the screen, which I think I will show you at the end of this section, if you will. However, if I were to use EDF and start stepping through, we would see about to execute command. Now notice, OD, MD, PMO. I know this is a put one call because it's using all three. The object descriptor is OD, the message descriptor is MD, and the PMO is the put message options. So open, put, and close in one call. That's how you tell what actual call is done. You notice there is no screen here that says, oh, by the way, this happens to be an MQ put one call. Unfortunately, EDF does not break that out. Okay, it basically shows me the parameters, and it shows me them in this nice display format with the periods being undisplayable characters. So if you really want to interpret it, you have to switch to hex. And by the way, these parameters represent the structures that I copied in. The OD, MQOD, the MQMD, the MQPMO. Unfortunately, it's not a friendly interface like if you're stepping through a CICS code in EDF where you can see exec CICS whatever. Because this is a call type interface and not the exec type interface, EDF doesn't interpret it. If somebody from Hersley happens to be here and listening, they can hear me say, yes, you could interpret this if you really wanted to. They would have to go into data areas though, as opposed to some nice standard DFH EI module to figure out the interface. But it could be interpreted. This is what you're going to see. Okay? About to execute command, command execution complete. Again, complete, right? Now, unfortunately, there's the comp code, there's the reason code. The last two arguments are always going to be the comp code and the reason code. They're in hex, so if you want to see how it worked, you have to switch, do F2 to switch from hex to character. Okay? And I didn't bother doing that. Okay, so unfortunately, EDF is a little strange compared to maybe what you're used to for the normal CSS type, right? Or even if you're doing exec SQLs or exec DLIs. The exec interface shows you. Unfortunately, because these are calls, not as clean and neat in EDF. Okay? Moving on, about to do a command. Now, this is an open call. And the reason I know it's an open call, I see the OD structure. Okay? Moving on, command complete. And again, it's the open call, and I'd have to actually look at the hex bytes to see what's good, if it's good or bad, unfortunately. Okay? Moving on. This happens to be a get call. The reason I know it's a get call, MQMD, MQGMO structure. The get message option structure is in use. So like normal EDF, I'm seeing command execution or about to execute command complete. And again, it's the get call that's complete, but I would have to get into the hex bytes to see how it works. Okay? The fun one. No structure name. Only one call does not have a structure associated with it. MQ close call. Okay? So this is the MQ close because there's a lack of anything like the OD, the MD, the GMO, PMO. It's the only way I know it's a close call. And of course, I would have to look at the first 4 bytes to see if it completes. Finally, I get my response back. Now, this takes very little time, to be honest. From the moment they would enter in the information on the screen till the time they get back this information, it's like a blink of an eye. It really is. It fires off a transaction in the background of CICS, the QT transaction that's working in the background. That gets a message, updates the DB2 table, puts a message, and wakes up this application and shows that the response coming back. So we can see the part, price, quantity on hand, all that kind of information. So pretty quick, pretty simple, but allows me to give something to system programmers to test with as they're working with tailoring and installing the MQ interface. Okay, statistics. If you're into statistics, this is what the printed statistics look like. Fairly straightforward. For the interval statistics, it does tell me the queue I'm working with. In this case, it's initiation queue for triggering. It tells me how many calls. It breaks them down to the various types of calls, you know, open, close, etc. You will never see the MQ con or MQ disk call to disconnect because CICS has done those in the interface. Okay, the applications will not do that. I wouldn't worry too much about the internal calls here or, you know, TCP switching. This one here could be an issue. Depends upon whether your applications are thread safe or not. MQ trues,
right? The true interface has to be thread safe. So it's using the open TCBs. You'll see that coming up here in a moment. Make mention of that. Basically, if your applications are thread safe, we don't have to switch TCBs. If your applications are still quasi-reentrant and you're doing MQ calls, it's about 5 to 8% extra overhead because it's constantly switching between the QR TCB and the L8, L9 TCBs. Okay. Next slide, you see these things over here. The only thing I point out normally are these. Single phase, two phase commit. I'll mention that again, you'll see later on. But basically, if CICS knows or has not been told by the queue manager that it's done any form of an update type request, it can do a single phase commit. Okay, if it has done any kind of changes to the queue, then it must be a two-phase commit. So it does a coordination difference, right? So it does separate that. The other ones I kind of look at, the ones up top, the first four as it says, would be if CICS, which should be zeros unless CICS was terminated abnormally. You got in-doubt units of work, right? Or you force terminate the MQ interface. I've seen people do that. And they create these in-doubt units of work. You know, you have to make sure you do normal warm starts to CICS or resolve in-doubts to resolve those. Okay, I mentioned that. And of course, the only other thing I mentioned is these last many lines were new calls that were added in MQ version 7. It's been a while. But they're brand new calls compared to normal processing, the opens, the puts, and the closes. Works with what's called message properties primarily, or publish and subscribe type processing. Don't find many people using those. Haven't found a high usage of these new calls compared to the old ones. And I've been working with MQ, by the way, for about 20 years. Okay, so I've got to beat my time here. Okay, important stuff. So interface. It is a multi-threaded interface, okay? So it kind of is going to take up many TCBs. These are the max open TCBs as far as the SI PARM goes. So you code max open TCBs equals some number. And by the way, at 5.4, the minimum you can code now is 32. You try to do anything less than 32, you get an error or a warning, and it goes to 32 anyways. What you're going to find, however, when I show you the actual resource definition here, is there's no way to limit MQ use. So these TCBs are also the same ones that are being used by any thread-safe applications. They're running on the L8s or L9s. The DB2 interface can also use these things, okay? But there's ways to limit those. You know, there's CICS parameters to limit the number of transactions concurrently using, you know, or running, if you will, of classifications. Or you can limit the DB2 interface, as I mentioned the last time I did this presentation, or did the virtual CICS user group, I did CICS DB2 interface. You'll see me talk a lot about the limits there. Here there are no limits. MQ can actually use all of your open TCBs if you let it. Okay. The other things is the interface. There is a CKAM transaction that automatically gets started up. It's referred to as the alert monitor. It's accepting special alerts from the queue managers, you know, like, hey, I'm shutting down, I'm quiescing, so CICS can tell the applications that this is going on. Mentioned the fact that it triggers, there's a trigger monitor task, CKTI, in CICS. That is the trigger monitor that's sitting on a queue waiting for a message to arrive that tells, you know, the trigger monitor, the CKTI transaction, which application to trigger. Now, in my case, I triggered the QT transaction, QT00. That's all being done by the queue manager, tells the CICS trigger monitor to do it. Okay? I won't get into all the details there, but it happens quite quickly. So here's the resource definition. Notice, I give it a name. I always make it the same name as the queue manager, MQAA. you are allowed to have only one active connected queue manager at a time. I can have many defined, but I can only have one connected at a time. Okay? Just the CICS limitation, the way it is. Same way with DB2, one DB2 subsystem. The only other definition is the name of the initiation queue for that trigger monitor to use. That's it. So it is using the max open TCBs, but I do not have a limit like I do in DB2. So it can actually tie up, many, many, many TCBs if it's allowed. Don't know how many of your applications are using MQ concurrently or how many are running concurrently, but it could be an issue to you. Almost wish there was a limit, but there's not. When I define a queue, or this is the queue for the trigger monitor itself, a couple of comments, and this again will be in your notes. It really needs to be shared. Those are MQ options. The default, by the way, on the mainframe, unfortunately, is exclusive. And that's because the application CKTI transaction, or I should say the trigger monitor transaction CKTI, and the queue manager need concurrent access to the queue. The queue manager needs to be able to put a message on this queue to wake up the trigger monitor, tell it what to trigger. It also should be defined as what's called delivery sequence of FIFO, first in, first out. You do not want priorities of messages getting into play here. Not that the queue manager is going to do it, but it can. Okay? So you really want FIFO here. Get rid of all kind of priority processing in MQ. By the way, I got a max depth of 1,000. There should never be a message on this queue. As fast as a message hits this queue, the CKTI transaction wakes up and triggers the application. The message, by the way, is about a total of 1,000 bytes. So I said, let me do max message length of 4,000. You can actually let it default to 4 meg, no harm, no foul. Okay? But 4,000, I can never see a trigger message going above 4,000 bytes. From IBM's perspective. Like I said, it's about 1,000 bytes right now, okay, in total. So that is the initiation queue. A couple of little tricks that help it make sure there's no hassles or delays, if you will, in processing the trigger messages. As fast as they arrive, that trigger monitor CKTI will start the CICS transactions. Here's my queue definitions. So my transaction queue that's doing the put one, you notice I said trigger type first, process definition to trigger, and I tell it which initiation queue to use. That's how I direct it. The results queue is going to hold the replies. Here's my process definition. I say I'm going to generate QT. Notice Apple type is CICS and QT. So the RT transaction I mentioned puts a message on the transact queue, which causes the queue manager to generate something called a trigger message and put it into that init queue. And then my QT transaction gets kicked off in the background, and it reads the transaction, updates the DB2 table, and then puts the results out to the results queue. So this is the queue definitions, right, necessary to complete my little transaction. Getting close. SVC dump. Now, if you're looking at a CICS SVC dump and you look at the MQ option, you're not going to see much information. You're going to see the queue manager name, its version, when it was connected. Now, there is a trigger monitor summary, CKTI. There's typically only one. Could be more. I'll show you in a minute. So it shows me the trigger monitors, typically only the one, that's all that's necessary. And then it has all transactions where it will repeat, but you notice there are no other transactions. So when I took this dump, there was no active MQ transactions. If there was active MQ transactions, they would show up in this list. The only thing I really look at is right here. Is the TCB actually in MQ? In other words, that task, is it running, and is it actually over in the queue manager at this point when the dump is taken? Pretty simple summary, okay? Not a lot of information, not a lot of necessary things. Now, I do show you data areas. So there's something called the INI block, and it's really for the initiation queue, the trigger monitor. These things have not been documented since CICS TS 4.1. That was the last time we had a supplementary data areas, okay, manual, okay, which IBM got rid of. Fortunately, they haven't changed a lot. There hasn't been a need to change a lot. So I still have my 4.1 manual laying around, okay? But not a big reason to go here. There's not a lot of information beyond. This life of adapter block is the actual MQ adapter interface. I do give you some offsets. I tell you, oh, by the way, here's the queue manager name, here's the CICS Apple ID, a few other little things. Most of what's in there is statistics. One last little block, life of task block. Now this is documented. It's hard to find, but it's the same format as the DB2 life of task block. Okay, the MQ interface was stolen from DB2 interface. It's all developed in Herzling anyways. The MQ interface, the MQ is, CICS is, and the DB2 interface and MQ is all coming out of the same laboratory. So this is actually the same format as the DB2 life of task block, which is documented, okay? Crudely, but it is. I give you some offsets in that, but essentially it's identifying the task. Now this just happens to be the CKTI because I did not have my user tasks at the time. Not a lot of information about the interface in the SVC dumps, okay? From the purpose of MQ, or the actual MQ interface itself. Okay, getting close to being done. There's a transaction, CKQC, that comes with MQ. And when you key it, this is the first thing you see. So I select connection first. And what I get is a pop-down display, start, stop, modify. So I with display. So when I do a display, I get essentially the current interface. It's connected. Here's the initiation queue name. Here's the queue manager name. I did have tracing turned on. There's only one in-flight task. To this point, we've done 4,300 calls. By the way, 81 of them, 4381 were okay. There's the number of opens, closes. So it's really the statistics as they currently are, right, in the interface. Again, you'll notice the single phase commits because the tasks that were being done, we're not doing any kind of modifications, if you will, to the queue. It wasn't necessary to do the, and that's because maybe, you know, they didn't do sync point processing on puts or gets, right? So there's no coordination necessary. You don't really update messages on queues, right? You can get a message and put it back to the same queue, but it's a new message at that point. So the real issue is, are your applications doing no sync point or sync point? And that's really what makes the determination whether CICS has to do coordination with MQ, okay? And of course, you can see the number of gets, number of puts ones, and because they are done with no sync point, there's no coordination necessary. Just the way it is, folks. If they were done under sync point control, then we'd see two-phase commits. So when you go back, you did option 3, and notice I can reset statistics, I can enable the API exit. I haven't bothered doing that. Question? Trevor's coffee.
Yeah, it's just a cough, sorry.
That's okay. Okay, if I told option 2, I can stop the interface. So again, quiesce is normal, allows task to complete, force will kill task. So I can actually stop the interface, and then if I did an option 1, I can start it, and I can use a different connection. So I can only have one at a time, but if I wanted to switch dynamically, I could stop the current one. If I had another MQ-con definition, I could then specify that one and connect to a different queue manager. But again, only one at a time. So I can use this transaction to stop, get statistics, etc. CKTI. Okay, so the CKTI transaction, I said, let me display it. So it gives me the basic information about the CKTI. And basically, it's currently task number 51. It's doing the get with wait on the queue, waiting for the queue manager to give it a message. Okay, that tells it what application to trigger. Not all that exciting. But I can stop the interface, right? and it goes through a normal termination, but I can also start. Now, I can actually start a second CKTI. If I wanted to, I can get a second one going by having a different initiation queue. Okay, so I could end up with multiple CKTIs running if I wanted to. I just have to start it with a different thing. Defining the interface, the MQCon resource that you saw earlier on an earlier slide, gives me one CKTI. When I start the interface, it starts one CKTI. I can use the CKQC transaction to start a second one or a third one if I wanted to. Different initiation queues is all. Last is the task display, and when I do task display, it gives me the same kind of thing. Here's the task. It does tell me it's waiting on a message, task number, and again, it's a get call. So that's the simple interface there, if you will. Okay? And I think that's actually, yep, it is, the last slide. So the interface is quite a bit simpler than the CICS DB2 interface. Let me kill my slideshow here. It is quite a bit simpler than the CICS DB2 interface, but I try to give you a lot of information about where to look and things. Kind of like a little summary. It is using the open TCBs, max open TCBs. There is no throttle for MQ, unfortunately. Okay, and there is, let me get rid of my PowerPoint. Get back to the thing. There is no way for you to limit those in MQ. So be careful about what you do when you start to define both the MQ and the DB2 interfaces here. Plus, take into consideration your applications that are thread safe. And I'm done.
Well, okay. Thanks very much, Tom. If anyone's got any questions, now's the time to type them in, and I'll ask Tom. I'll just give people a few moments to
Sure.
to start typing, and we'll just see. Well, Tom, can you just remind us of your email address in case anyone thinks of a question afterwards that they'd like to?
Yeah, I didn't have a last slide. It's Tom D, T-O-M-D, at Themis Inc, THEMISINC.com.
Brilliant. So yeah, if, otherwise people can email me. My address will be on screen in a little while, and I'll pass them on to Tom, and I'm sure he'll get back to you fairly promptly with the answers. Have you got any questions? Okay, well, oh, there we are. Let's see. There is a question. I just can't access it.
Well, I see the one there talks about standard and special trace. Well, it's a standard tracing options, okay? And what gives you the information in a trace is actually MQ level 1 and 2. And that's why you see the queue name, right, and all those calls being done. So it's the MQ 1 and 2. And that's why you see that. Special tracing is if I did a tracing by, you know, a specific terminal ID or, you know, specific transaction.
Okay.
Go ahead. Sorry.
No, you finish off your answer, and then there is another question.
Jan says something about closing the resource that we open just for a matter of keeping things clean. Can do that. You can do that. Most applications are only working with 1 or 2 queues. I have seen an extreme where an application was using like 30 plus queues in one particular task. And not closing the queues did save a bit of time. And there's no reason, unless they're doing exclusive control of queues, is really not necessary to close the queues. It's not like closing a file.
Okay, yeah, thank you for that. Okay, while we're waiting for anything more to come up, I'll just make myself presenter. Okay, and I'm going to share my presentation. Right. Okay, well, yes, thank you very much, Tom. And as usual, just assume that that the whole of the audience are giving you a virtual round of applause. So thank you very much for that. Okay, I've just got a few slides to run through, so let me do that. In the news then, Dynatrace has announced that it has extended Dynatrace, its AI-powered platform, to include IBM Z support for CICS, IMS, and middleware. This gives customers, they say, precise information about the performance of digital services across hybrid environments, from cloud applications to the mainframe. Dynatrace provides software intelligence to simplify enterprise cloud complexity and accelerate digital transformation. It provides end-to-end visibility by automatically discovering and mapping every transaction with a single AI-powered solution. So if you're interested in that, there's a link to it from our website, from the news page. So articles, there's been a few. We've got all new Node.js in CICS trial now available. That's by Natasha Mackenzie Kelly, and that's on the CICS Dev Center. We've got new enhancements to CICS Performance Analyzer version 5.4.0 by Satish Tanna, again on CICS Dev Center. Managing enterprise-wide deployment of CICS Explorer by Dave Nice on CICS Dev Center. And check CICS health quickly with IBM CICS Statistics Visualizer by Vera Chen, and again on CICS Dev Center. And there's links to all of those from our webpage. As always then, can I ask for feedback about this meeting? You can comment on anything good and anything you think we can improve on next time. And you can email your comments to me. My address is on screen at the moment. And there's also the Contact Us webpage on our website if you want to use that. So, plan for the future. Our next meeting is on the 9th of July. We've got Colin Pierce back again, and he'll be looking at how to solve CICS NQ problems. And then the meeting after that is 10th of September, and we've got Glenn Schneck, who's Principal Technical Architect at GT Software, or you might know him from the CICS stream at Share. So, two interesting ones coming soon. Just a reminder that you can keep up to date with what's happening in the world of CICS and on the virtual CICS user group website by following us on Facebook and Twitter, or by joining the virtual CICS group on LinkedIn. And the URLs are all on screen, but they're also on the homepage of our website. We like lots of likes, and if you do tweet or anything, then the hashtag to use is hashtag virtual CICS. So that's all for this meeting of the Virtual CICS User Group. Can I thank you all for attending? I must thank Rocket Software. They're the people who sponsor this user group and make these meetings possible. And of course, I'd particularly like to thank Tom Dunlap for his presentation. So that's it. Thank you all very much for joining the meeting, and I look forward to seeing you on Tuesday, the 9th of July. So thank you and goodbye.